Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this is the title from motion capture of interacting hand to video-based rendering. I tried to fit all together in this talk. So let me start with this slide. So this is the kind of the big picture I've been working on since my PhD studies. So I wanted to start with this. So at that time when I started, there was a lot of interest in generating free viewpoint video content out of input videos. And this is the typical pipeline that you will use for generating such data. You start from input videos taken from a scene from multiple viewing angles. You calibrate and synchronize the videos. Then you just use some 3D reconstruction technique to get a mathematical representation of the scene. And then with a bit of effort, you just apply some video-based rendering technique and you get the desired free viewpoint videos like in this case. So at that time, our first attempt to do so was to build a body scanner. And this is just to make you a bit laugh, because at that time we didn't have so much money and there was no Kinect, so we built our own body scanner that actually worked like this. It was an hardware that was enabling to take picture all around. It was the turning table, in practice, the rotating turning table. But the person has to be static because otherwise, for inertia, it will move. So we rotate the entire studio together with the camera and also the blue screen, so that we will have always the captured images with a blue screen behind. And obviously then we apply well-known technique like variational approaches based on silhouette and photoconsistency to get the shape of the person. And then we texture it using some wavelet-based blending technique. But this was only for static object, right? So to deal with dynamics, what we did, we built a recording studio. This is the kind of studio that probably you're familiar with. We had at that time 4 cameras working at 21 frames per second with a resolution which was slightly below 1 megapixel. And we captured some performances so that the problem for our problem became given the 3D model of a person in a static pose like this one, and the videos recorded by these 4 cameras showing fast motion, motion blur, and a lot of occlusions like in this somersault sequence. Our aim was to estimate the pose of the person at each frame, and so that in the end we had our free viewpoint video content that was this one. And so this is well known. I mean, there is a lot of paper about this thing. And at that time, okay, we say, okay, there is a lot of work about this kind of things when we were thinking, what about doing something more challenging? And we were thinking, what will happen if we have people interacting with other entities, for example, with balls, with a rigid object like in this case, and we modify the algorithm to deal with such things. And here I want just to spot that there is no collision detector, so I mean there is no prior information about the fact that the ball should not enter inside the person. But this is the kind of result that we got at the beginning. We moved forward to try to deal with 2 persons, like 80 degrees of freedom, always dealing with 4 cameras. And this was what we were obtaining. And then we move also forward to people interacting with each other and with object, like in this case. And this is what we were able to capture, stealing 4 cameras and about 83 degrees of freedom. We didn't estimate the rotation of the ball because it was too blurred, but I mean, hypothetically one can also estimate such a thing. But still with 4 cameras, so there was a lot of lack of information. So at that time we tested in multiple scenario with a lot of motion, with a lot of spanning a lot of different kind of motions, and everything works fine. We didn't need. I mean, it works pretty well in all the sequences that we tested, as long as the two persons were distant between each other. So when the two persons were closely interacting with each other, there was some problem. Like in this case, I mean, we were absolutely not able to deal with people hugging, dancing together, or we didn't test it, but I mean, I think that this is the rugby scene that you can see here is the most challenging scenario one can apply markable motion capture to. Especially, I mean, I will imagine that one day we can track these players jumping one on top of each other, and that will be pretty cool. But at that moment, we were not able to do that, and neither now. But at that time, when we saw this, that we were not able to deal with close interaction, what we did, we paused the research until we figured out that there was a more challenging problem to tracking closely interacting people. That was tracking closely interacting hands. And the two things have some similarities, because when the people are interacting with each other and the hands are interacting with each other, you have a lot of collisions and you have a lot of occlusion that generate lack of information. And beside that, the hands has the additional challenges of the self-similarities. While in fact it's easy to distinguish a head from a foot, it's very difficult to distinguish the different fingers given the image. It's difficult to distinguish the pinky finger with the index finger, but also difficult to distinguish two fingers belonging to two different hands. And beside that, they have a lot of lack of, they have a sort of lack of texture, especially if your camera is not high resolution. And so we were thinking that if we are able to deal with tracking hands interacting with each other, probably we will be able to also to deal with tracking closely interacting people. So when we look in the past work about hand motion capture, and we saw that most of the work was focusing on single hand in isolation. And while instead there were some few works about hand interacting with an object. But they mostly rely on the assumption that the hand can be segmented from the object based on color, because it's a hand. So I mean, they were using hands, skin color to segment the hands, which actually simplified the problem. But obviously, actually there was also a similar work for closely interacting people, which actually Liu et al. 11, that was exploiting the same thing. It was just trying to segment the two person and then just apply pose estimation kind of independently between them. However, with hands, with interactive hands, you cannot apply, you cannot use this assumption, because the hands cannot be distinguished based on color, because they have the same color. So to deal with this, what do we do? First, I will recap the problem, what was the problem of tracking interacting hands. As input, you have a scene recorded from multiple viewing angles, depicting some hands interacting with an object. And then you have a template model for each of these objects in the scene, together with their kinematic structure underneath. And the objective was to record the scene motion in terms of joint angles and position of each element of this kinematic structure, so that at the end you have either the full 3D geometry of the scene or our desired viewpoint videos, as we wanted at the beginning. So how do we do it? So our first assumption is that whatever object is on the scene, whatever object that we wanted to track, can be approximated as an articulated deformable object. It has like a surface or some mesh that deform according to a skeleton that is inside, like a hand, for example. And we approximated, in case of the hand, the skeleton using 20 bones for a total degrees of freedom. Here you can see the degrees of freedom that we use. So it's slightly more than the standard hand model. And we parameterize this pose using exponential maps. Actually, if there is some doubt, just ask me questions during the presentation. Then what we did was just we recovered the model or the mesh of the hands on a reference pose, in a static pose, like we did for the person, using multi-view stereo, but one can also use Kinect, but in our process we use multi-view stereo to do that. And then we model the deformation of these hands using the linear blend skinning operator, which actually is this formulas. And I mean, it's in practice, it defines the motion of a vertex as the linear combination of all the motion that the vertex will undergo if rigidly attached to every bone one at a time. This is what the formula says. But the result of this formula is that it provides you a smooth deformation of the mesh accordingly to an underlying kinematic structure. And this deformation is guided by some weights, this alphas here, which is a matrix, and which looks similar to this one, which we assume to be known a priori. Or one can also estimate it using these approaches, but I mean, for a hands, it's fine to assume it a priori. Then when you have such a model, the typical approach to do pose estimation of hands or people in videos is either to use a discriminatory approach or a generative approach. So the former actually aim to learn some map from images or part of the images to a pose, while the second one is do exactly the contrary, and is just perform a maximum a posteriori of the probability of the pose C given the images, which actually translate in an energy minimization, right? And where the first term here is just the likelihood, how much the pose match the images, and the other is the prior informations that encode joint constraints and other stuff. This is just to summarize the pro and the con. Typically, the discriminatory approach is more robust, while the generative approach is more accurate. Generally, somebody can have something, but in the framework of pose estimation, in both cases, the solution is not unique, because you have a sort of multimodal distribution in a sense that you usually do not have enough information to infer the pose. You usually have some ambiguities. The generative approach has also inherited all the functional minimization problem. And the funny thing is that this functional is typically non-convex, so minimizing it is pretty tough. Nevertheless, in this approach, today I'm going to present a generative approach, which actually I will present some energy to minimize, but at least I will provide an energy that is differentiable, which means that at least I can apply local optimization to it, which, however, it will be still non-convex, highly non-convex. So what we did, so following the generative model paradigm, I mean, what I discussed before about the model of the hands provide the generative model, which actually tells how the hands will look like at a given pose Xi of our skeleton. And by comparing this with the input images at specific time t, we have that the pose that we are looking for is actually the one that minimized this comparison error. Or at least that the pose that we are looking for is one of the global minima of this comparison, assuming that our comparison function is correct. And typically, the people past work, what they did is they perform this comparison in the feature space. They don't do image-based comparison. They just compare in the feature space. And the typical features that they use is edges, optical flow, silhouette, depth, shading, and texture. These are the possible way. So edges, as you can see here, probably provide a fairly good cues about the hand displacement. Optical flow instead provide a sort of temporal continuity because it's kind of forcing the solution to have the same optical flow as the measured one. And silhouette instead is some sort of subset of edges. So it's a kind of lower information, less important information than edges in practice. Depth, shading, and texture are very good cues, but to have depth, you either need a depth sensor or you need cameras with small baseline. And instead, shading and texture, you need prior information, so where the light is, or you need the texture of the hands in practice. So in our approach, we started using edges and optical flow for this reason, because we didn't have this kind of additional information. But we soon realized that these were not sufficient because when hands touch each other exactly during the interaction, edges disappear due to color similarities, and optical flow is not able to compensate with that if this lasts for multiple UV. Tell me.
Quick question. How many, what's the input sensor you have captured during test time? Is it just
cameras?
Just one camera or multiple?
Multiple cameras. Okay. And optical flow was not able to compensate if this lasts for multiple UV frame because somehow optical flow is sensitive to drift. So if this lasts for multiple frames, it's not no more reliable. Therefore, an additional stronger visual cue needs to be used for estimating the hand pose. And we did this by using salient points. So we actually learned the appearance of some characteristic features on the image, on the hands, and we detect them on the videos. And in particular, we detected fingernails, but one can also detect knuckles or other parts. Well, probably fingernails and knuckles is the most characteristics. But then we observed that due to the self-similarities, we were not able to learn, to train a classifier to distinguish also between nails of different fingers, because they look very similar between each other. And tracking in general did not help because there will be a lot of occlusion. So we completely avoid to use tracking, and we rely only on the detector for each frame. And so that in the end, what we have, given a video frame and some detection found by the classifier, we knew that this detection were in a one-to-one mapping with the vertices corresponding to the fingernails, but we didn't know this mapping. So to find it, what we did is just we take all the detections and we superimpose with the hands, the video frame, with whatever best estimate we have of the hand of that pose, like initial estimate for that, or maybe taken from the previous frame. And we build a distance matrix encoding the distances between these detections and the finger and the vertices on the fingernails. And here in the image, you can see that low distance is encoded as a white box, and the high distance is encoded as a darker box. And so clearly the most easy way to do it is applying closest point association, that this is what it will correspond to. And if as you may notice, I mean, if the hand is slightly off, this will completely generate the wrong correspondences. Therefore, a better way to do this is to just find out the correspondences, the association, which actually is one-to-one association, which minimize an aggregate cost of the selection. And this actually provides the correct correspondences. However, we need to deal with the fact that the classifier is not perfect. There will be missing detection. There will be false detections. And to deal with those, we just added to our matrices one additional column and one additional row, indicated if selected that the correspondence vertices or detection has no match. And this actually provides the correct association, as you can see there. And all of this is simply a bipartite graph matching problem without layer, which is actually translating an integer linear programming problem. And okay, so given this, what we did, we took all our input videos, we extract edges, optical flow, and salient point, and we did the same for our generative approach. And then instead of comparing this information together, which will lead to a non-differentiable function, what we did is, since we have some sort of correspondences between mesh vertices and image point founded by using the salient point, we compute the same also for edges and optical flow. And this allowed us to formulate the pose estimation problem as simply as the minimization of the reprojection error of the founded correspondences. And this is a nonlinear least square problem where each term is differentiable. You see here, this is the standard projection function. This is just the linear blend skinning. It's easy to derive. And for this reason, we choose to optimize it using level marker. However,
sorry, the silhouette correspondence is also found using the integer program.
no.
No.
I can show you here. So that is kind of similar to ICP. So here I have an example with the, so it's a kind of 2D ICP plus a shape matching. So in practice, for each vertex you projected on the image, we look at the closest edge which actually looks similar. So we have a sort of shape matching. For example, this was the ball and the feet. So I mean, these two edges look similar, so I create a correspondence like this. It's sort of 2D iterative close point problem. And obviously, this is the comparison with distance field. Why distance field? I mean, why we didn't use distance fields? I mean, the thing is that distance field will generate even more local minima. So, so this thing, I mean, however, using reprojection error, this kind of functional has two main problems. One is that this is norm 2. So this means that we are implicitly assuming that the error in these correspondences is Gaussian, which is clearly not Gaussian. So we need to absolutely take into account for outlier. So we just have an outlier detector that gets rid of whatever is out of the Gaussian model. And this is very important for the silhouette and the optical flow correspondences. A bit less important for the finger correspondences because there are very few. And the second main problem is that the initial correspondences might not be correct. Therefore, we kind of solve for an alternating minimization scheme. So where we, given the image, and the best estimate we have for the pose, the initial pose estimate, what we did, we solved first for the correspondences, given this pose, and then we solve for the pose by keeping fixed the correspondences, and then we iterate until convergence. If this gets stuck to a local minima, we initialize the entire process using simulated annealing and then rerunning the entire iteration. So, however, due to lack of information of overfitting, that optimization scheme might lead to solutions like this one, which we know that are not plausible in reality. And to cope with this, we just added an extra term to the functional to minimize, just to take into account for collision and self-intersection. And this one, actually, what we did is that at each iteration, we just found the colliding faces, and for each pairs of colliding faces, we just generate some local distance field between these faces that penalize the collision of the self-intersection. And we make sure that this term is actually a least square term. So the usage of distance field allowed us to have this as a least square problem so that we can still optimize it using level marker and it's still differentiable. So we tested the algorithm in different scenarios. These are very few. This is some examples. So the input videos is on the left. The estimated pose is on the right. And here you have the estimated pose superimposed with the original video. So here we had 8 cameras recording at 50 frames per second. And the total degrees of freedom was 70 here that we were estimating. And here is a case with strong occlusions, for example, because I mean all the cameras were placed in a circle. And so most of the part down here was not estimated correctly. So the idea is how do we handle additional object in the scene? So I mean, since the algorithm adapt with that, I mean the idea was that whatever additional object you have, you just need to scan it and get a 3D model of it. You just add skins like the skeleton and the alpha skin. And then you just need to add it to the kinematic structure of the scene. The nice thing of using linear blend skinning is that the linear blend skinning will treat these 3 objects as a unique one, because at the end the alpha the alpha matrix of the skinning parameter is just a block diagonal matrix. And this is kind of a unique object where the root bone is connected to a virtual scene bone. And this allows us to use the same algorithm as it is, and you can handle collision and occlusions between different objects as self-collisions and self-occlusions in practice very easily. And so this is an example of the ball that you saw at the beginning. And I skip it because you already seen it. I mean, so there are still some problems. You see that there are, when the hands were trying to grab the ball, they were a bit off. Or it works fairly nice. And this is an action of taking off a ring. So the object is pretty small, and this is pretty problematic to track. And this is an action of paper folding, where also the object was deformable. So here we have 78 degrees of freedom, I think, in total. I can check later.
So that's 8 for the paper.
Let me check. So it should be 8 for the paper. So this is how we skin it. So obviously we cannot track all the possible deformation on the paper. But I mean, there is a position, a global rotation. So it's 3 plus 3, 6, and plus 2 degrees of freedom left and right. So it's 8, yeah. Okay, this is the conclusion. So the conclusion of the first part of the talk. So, I mean, we were able to handle with articulated motion of hands, 78 degrees of freedom and a lot of occlusions. We use salient point, distance field, and matching problem to deal with the collision, the self-intersection, and the self-similarities. And so we had also a comparison, a quantitative evaluation with respect to oikonomidis that it was here, I mean, what I heard. So in their approach, they were using actually, it's still a generative approach, but they didn't have a differentiable function. So they were solving using samples, and I think it was around 2,500 samples per frames. They were working pretty fast. However, it's still a sampling technique, so obviously local optimization has an error which is below a sampling technique. In this case, was 3 times more accurate. And this is still what we cannot handle. So hands interacting, but a sort of hands wash sequence. Actually, we tried in one sequence of the hand wash, it worked. In the other, not. So we just say that this does not work. And we tried also with PSO, with the oikonomidis work, and it didn't work at all because, in a sense, also a sampling approach is not a global optimization. It's just it's just doing a local optimization with some sort of robustness with local minima, but it still fails in local minima in this scenario. And obviously, I mean, a possible solution could be to use post-prior, which actually we don't use at all in this work. And then, okay, so I mean, this, I just want to ask if there is question for the first part. I mean, there is all the data set and 3D model is online, and there is also a 3D Max plugin. So the 3D model of the hands, and there is also a 3D Studio Max plugin if you want to create your skin and model and export it and use it in C++ somewhere. Yeah.
So a couple of questions. One relates to in the sequences there were 4 cameras, right?
In the mock-up of the person there were 4. Here there were 8.
8. And
yeah.
Did you basically look at how the accuracy changed with the number of cameras?
Yes. So wait a second. Is it here? Yes. This is the 8 cameras. This is the mean joint position error. Mm-hmm. So this is how it works. So with 5 cameras, so I mean with 8 we are something like 1.98 millimeters. And then with 5 we are still at 2.5. With 4 it's 3.5 millimeters in average error. It increases. It goes up exponentially, right?
And what about how crucial is the segmentation? For example, at the moment you're assuming pure segmentation. Now
yes, I have a black screen, right?
So yeah. So your random forest classifier, the one which was giving you your initial detections of the fingertips and so on, you could as well as sort of simulate artificial backgrounds and then see how that would affect.
If you mean outlayer on the detection, you mean?
Yeah. Basically, at the moment the segmentations
It's
are
perfect.
known, right? The segmentation is what is given to the random forest sort of cluster, which actually detects which fingertips there
Yeah,
are.
so we
right?
are not running the detector in those. I think we are running it actually, but I mean it doesn't make sense because it will never detect something there. So there could be outlayer outside the hands, yes.
So the question was essentially how robust would it be, how robust this approach would be when you are dealing with non-segmented hands, right? And you just are given an image, and how crucial is the segmentation for computing the correct correspondences?
Well, so I don't think so much. Let's see how I can convince you. So, well, first we are using edges. So assuming that if it's all cluttered behind, so well, probably you have a problem because a lot of edges will appear. And that is the first problem that will come up. Because, but if you have a homogeneous, not homogeneous, but reasonably normal background, it should work. Considering the detection, how robust is the algorithm to outlier in practice? Is it that the question in practice? It's kind of, right? Because if you have a lot of detection outside the hands, you will say, okay, one finger should go there, right?
Yeah.
So, and that we are trying to deal with the graph matching problem, right? So we are assuming that we just penalize, actually, where is the graph matching? I can show it to you here. This one, right? So these are the kind of things that guide your outlier, so that penalize things that are far away in practice. If you are unlucky, it can break up, yeah. It can break. I would say a better way is to do detection plus pose estimation at this point. But it can. So obviously, also the detection is one information, but then there is other information like optical flow and edges. So if one of the detection, one finger will say, okay, you have to go upper right, you hope that there is enough information to say, no, that does not make any sense, and this will be marked as outlier.
Can you just show us the edge map again?
I
Close
don't.
to here, isn't it?
I don't think I have the edge map that I have. I think, okay, this one.
Okay, so you do get these interior edges.
Well, sure, yeah. That is the idea of having, yeah, that is a nice thing. So actually this was, yeah, I have a personal implementation of the edge filter, so this is the only one thing. It's not the standard OpenCV. You don't get this thing with the OpenCV. But you have also fake edges, like this thing, which is not something. And this one is a double edge that is due to the shading. So there is some outlayer also in the edges.
Yeah.
So, but since you have multiple cameras, it should not bother so much. So we actually tested the algorithm. We didn't test it on the presence of outlier in the detection, but we tested on, actually it was this one, we tested on the presence of how much the detection was working. So this is the detection rate. You see that at 100%, if it detects all the finger, it's still 1.98. But it still works nicely if you have 30%. So edges and optical flow are still a strong cue.
And 0% detection is the same as having 3 cameras.
So 6? Yeah. Nice observation. Yeah.
Another question.
Yeah.
Okay. So, Archimedes also in CVPR this year showed 2 hands
Two hands, yeah.
interacting with one another. How come that approach? Because I think that used skin tone as one of the metrics for segmentation. How did that work so well?
Yeah, well, they use depth data there.
It was the Kinect camera.
Yes.
Yeah.
So depth is a very strong cue. Very strong. And secondly, I mean, I only saw it actually. I mean, I need to talk with him, but I only saw it during doing this kind of things. And the accuracy of that pose estimation to me is not convincing. Then it's all a matter of opinion, but somehow you cannot see very well if it's really working well there. I mean, it's overimposing, but I mean, it's. I mean, I would like to see it running. I don't know if I mean, there currently not a demo that works on two hands, right? So that could be.
So two follow-up questions. One is, you've got a multi-view camera setup.
Mm-hmm.
Did you think of using depth in your system, and then?
Well, I cannot do multi-view stereo in that case. I cannot do stereo because the cameras are, in any case, even if there are 8, there is not enough. The baseline is pretty wide, so I cannot get depth.
Could you not do wide baseline matching? Or?
Sorry?
Can you not do wide baseline matching to get depth? No?
I don't think I have enough texture. I tried with a simple texture, with a simple stereo algorithm, it didn't work.
Right.
Well, I don't know, maybe an idea could be. I mean, if I put the camera a bit together, I mean, the nice thing will have to have a couple of cameras. So you have 4 cameras, but 4 depth cameras.
Mm-hmm.
Yeah, that could be an idea, yes. It's like having 4 Kinect all around. That is a very strong cue, actually.
Very high resolution cameras and basically get a person with freckled hands.
Yeah.
Maybe then you will get a lot
Well,
of
super high
performance.
res, you're fixed.
Yeah,
Super
yeah.
high
Everything
res
is-
with fixed.
People, humans have built-in connect pattern if you're super high res. I'm really sorry, I've got to run,
Okay.
but I'll catch the rest on video.
Okay.
And you thought about trying this with Connect as well. Have you
So,
done
yeah.
any experimentation?
I try it, not with hands, with humans. It works. I mean, it was for another project, but
Mhm.
yeah. I mean, it's pretty easy to have a I extend the generative model to depth, right? I mean, it's very easy. And also it's differentiable also, so it's...
Do you use the other features as well as depth, or is it just purely depth-based features?
Yeah, no. It's depth, edges, optical flow, silhouette at that time also. And yeah, that worked really well. Yeah, obviously it has always the problem of initialization. This is the main problem of local optimization.
So, 2 questions, I guess. Did you have a view of the hands from that's not from one of the original input camera viewpoints? Because
Yeah.
generally that's where it works.
The hands, the 3D hands. So let's start with this one. So this was with the camera view. So this is one. This is actually the. Oops. Or I can show you another sequence here, actually. Wow, I cannot exit here. No, it's problem of keyboard. Okay, I found it. Let's say this one. This was the. So you see that there is still some ambiguity. Oh, here you can see also, wait. Here there is. So actually we tested multiple times these sequences, so this is one of the results that we got. But you see that since we are collision as a soft constraint, you see compenetration here. This is also due to the fact that this thing is very soft. So I mean, if you are doing like this, it's probably changing a bit. And this is not. This is an. Oh, this was the ball. It's pretty difficult to use this. Ouch. The ball is very challenging, especially when it closes, because you don't see under it. And there you see that there is some ambiguities in the pose. Yeah. And also it's floating. So one idea was to use some physically based constraint pose model, because I mean the nice thing would be, I mean, I don't know, I mean, it's possible, but the idea is that the ball will fall down if you don't hold it, right? So you can exploit this kind of things and say, okay, there should be a contact. And well, any other questions? Or
I guess one more is, what's the frame time for optimizing one frame?
optimizing one frame, it was around 20 seconds per frame.
Okay, so,
So
it's not quite real time yet.
No, it's not real time at all. And no, I was talking also before with Taylor. I mean, the thing is this one, we were using, I think you can push it because the dimension, the size of the hand model was pretty high. Also, the video was full HD, and one thing that you can do is zoom on the interesting part, decrease the number of vertices. For example, the pose estimation for humans that I showed you before, that works 1 frame per second during the estimation, because it's just less vertices, and the resolution of the camera were smaller. So in that case, it works faster. I mean, the bottleneck is clearly the level and mark art, which actually I didn't implement it. So we were talking before to use a sparse level and mark art, which I'm not using it currently. I'm just using the Lurakis out of the shot. Other questions? Okay, how much time I have? Okay, I speed up and I'll try to do fast here. So, I mean, coming back to the big picture, I mean, that we had this idea of using free viewpoint video content. So, what I presented could be seen as a way to generate free viewpoint video content of hands, or you can think about also humans and other things. But you know that there is a lot of methods that generate free viewpoint video content, and this is some of them. However, most of them works in indoor environment where everything is controlled from the camera, which are static, to the lighting and the background, which is controlled. So, some of this work I've tried to relax this thing by using this constraint by using large number of cameras, or scene prior like we did before, using a template for the object in the scene. However, what we want to solve is that how can we generate free viewpoint video from videos which are casually captured from people with their cell phones, with their camcorder when they go to an event, such this guy in Covent Garden, and they record this event. And here what we have is that we have cameras that are moving, we have large uncontrolled environment, and they are filmed by non-professional people because you cannot predict what they do. And this is kind of part of a broader vision where you have a lot of, when you go to an event like a concert or something like this, you have always people with their cameras recording it, and most likely these people will just upload the videos on YouTube. So we think that in the future you will have a lot of these videos online. And as PhotoSynth does for picture, what we wanted to do was to do the same thing with videos, right? Navigate a video collection. And this is something that we were thinking because these videos does not belong to the person who just record them. They belong to the event. So this is what we want, an event-centric visualization of this collection of videos. And so what we wanted to propose was something like this. I can show you. It's an interactive system that works like this. So this is kind of a Windows Media Player. Let's call it like this. So you have the standard timeline control, but then you have a spatial navigation control, which says where you can go and where are the next cameras. And you want just to make a transition with them and see it from multiple viewpoints and change also the audio and see what is happening from other point of view. This is actually running on my laptop, actually. So, as PhotoSynth did, we copied a bit the pipeline. In a sense, we took the video collection and we just made an offline processing, which generate the metadata to visualize this thing in our media player. And this offline process just aim at calibrate the video stream and segment the main performer. So what we did is that during this offline process was just we bootstrapped this process by applying structure from motion and multi-view stereo to some images of the scene where this collection was filmed, either video frames of, from the videos or picture from Flickrs or some other internet sources. And we get a 3D model of the scene, and then we texture map it. Then what we did, we took the video collection and we synchronized using audio. Obviously, audio has some problem. You can use other visual cue. And then what we did, we color calibrate each video stream with respect to each other and with respect to the textured geometry. Then we spatially calibrate each frame in each videos with respect to this geometry. And to do this, what we did is we established correspondences between the frame and the images that we use to reconstruct the 3D geometry. And since these images are calibrated with respect to the geometry, you have a sort of 2D to 3D correspondences, which you can use to estimate the pose of this frame inside the geometry using direct linear transform with ransack and then a geometric refinement minimizing the L2 geometric distance. But obviously, as you know, everybody that has worked in augmented reality knows that this stabilizes only sparse feature point in the image, and it completely neglects the rest. So if you have features in some portion of the scene, you have a stabilized image. But if you don't have features, there is no way that image will be stabilized. And this is a problem when you augment the original video with a synthesized one, like in this case. I mean, you might notice here we are just superimposed the original video with a synthesized version of it. And you can see some flicker here on the ground, which is exactly where there is typically no correspondences because the perspective artifacts are the perspective artifacts are too big. So what we did, we refined this calibration data by just minimizing the residual. So we take the original video and synthesize one, we took the difference, and we optimize the pose estimation by minimizing this distance, using an L0 minimization, and this is what we got at the end. So as you can see here, there is no flicker and it's more stable. So it's a kind of calibration not based on features, but based on all the points in the image.
So there was no temporal sort of priors as you were sort of calibrating, because it was a 2D to 3D sort of correspondence.
So, yeah,
you use the priors on camera motion and stuff.
We were using that using the refinement. We were using also prior, some continuity.
Mm-hmm.
And you also, by minimizing this L0, since it's based on sampling, we were including also sample from the previous frame. So there was some sort of continuity.
Which is implicitly enforced, right? Because your sampling process only generates correspondences which are, in some sense, from
correlated with the time -1. Yes, yeah. So, but there was no smoothness term in practice, but there was just an optimization where we started also from the previous frame. Then we performed the segmentation, and as many of you know, that segmentation is very basic when you have a per pixel color model for the background. But in our scenario, in a casually captured video scenario, the background is changing, so the people are moving in the back, and also the camera are moving. So what we did is that first, at least with some help, we just asked to the user, just draw some stroke where the person is, like in a grab cut scenario. And this was a maximum 2 frames per stream, not even lower. I mean, it doesn't scale by the number of streams. So that we got a color model for both the background and the foreground. However, if you apply this color-based segmentation based on this color model, this is what you get. And this is due to the fact that most likely the skin color of the main performer is the same as the skin color of the people that are looking at it. And this is clearly useless as segmentation. So what we did is that we use this as a conservative segmentation by saying that everything here that is black is for sure background, everything that is white can be background and foreground. And we actually use this information to generate a per pixel color model of the background. And this is similar to the Chang et al. Approach, the video matting approach, where we actually retrieve the color of what is missing in one frame by looking forward and backward in time for a pixel which represents the background in practice. And we can do this because we have these videos calibrated with respect to geometry. So we have a sort of, we know exactly where is the light field, so we can always reproject it in each image. And we use this model to get a better segmentation of the performer, which is still not perfect, but still is okay. But all this part is normal vision technique, a bit. We just design it in such a way that it's more robust for these casually captured videos. And this generates the metadata that we used in the navigation system. So the navigation system, it's particular, but I mean the initial part is pretty basic because once you are attached to a camera, you just display the camera and everything is fine. But the problem is that when you want to when the user requests for a transition from one camera to the other, so the system has to generate the intermediate views between the two cameras. And we actually did this by modeling the background, the background as using the pre-computed texture geometry, and the foreground using billboard clouds, so a billboard for each camera. And obviously, the background is always better to not use the texture geometry. It's always better to use an updated geometry. In this case, we use a structural lumigraph to render the background. Here you can see the two camera sources, the background geometry, the way we blend it, and this is the final result of the background. And instead, the foreground, that is the main contribution of this work, is the foreground is modeled as billboard, but billboard has a very big problem. That is, when you are transitioning from one camera to the other, you will notice a sort of jump, right? Because the billboards are flat, and this is due to the fact that this jump is due to the fact that the two billboards at the moment of the switch, they actually represent two different sides of the performer, like you can see here. And so to deal with this, we just did a trick. And so since there is a user in between, and the user is requesting for a transition, the system, instead of transitioning right after the user requested, it just waits, and in parallel to the playback, it just computes the best moment to make the transition. So it's a sort of video texture approach, where we try to minimize the artifacts that are visible by generating this unperceivable delay in the system. And so this is actually what we found. And the idea is that these perspective artifacts should be hidden inside the motion of the performer. Like you can see here, this is actually the optimized transition. This is something like this. So we want that perspective artifact is perceived from the user as a motion. And we did this by using this interbillboard distance, which is actually what we did is the best moment to make a transition is where the silhouette seen by the observer at the moment of the switch should look similar. The more similar they are, the better, the less artifact you will see. Obviously, I mean, here they're similar. Here is a bad moment to make a transition. And this has the extra benefit that since our segmentation and calibration process is not perfect, this actually takes into account of that, because in that case there will be a big distance and so a bad moment to make a transition. And so actually here there is a comparison between unoptimized and optimized. You have to look before this one and then this one because this is delayed. So try to see it before left and right now, left, right, left, right, left, right, left, right. So I can show you also a demo of it. I mean, this one was the Covent Garden. I've never been to Covent Garden, but Gabriel was filming this. So this is actually, if you have already seen this guy. So Actually, this is the geometry that we have recorded for Covent Garden. These are the cameras. They are moving just a bit because there was too much crowd there at that time. So this is the transition that we can have here. So obviously it does its best, but the idea is to give the user the sense of orientation and do not get lost while transitioning. Oops, no, this was an error.
Okay guys, get ready to clap please, get ready. After this, 3 chainsaws.
Okay, wait, there is another one that is, so this one was outside our building. Here we have 6 cameras actually, widely moving. Oops, so here you can see they were also switching, so it's a bit of a mess. The audio here is not... Somebody might recognize Gabriel. Voice. Oops, a bit of delay. It's trying to do its best. Okay, it doesn't like a transition. Obviously there is parameter to set, but so this works in these scenarios. I mean, what are the limitations, the main limitation of this kind of things? That is still performing centric at this point. So it can handle a certain amount of person because you need to distinguish this person inside the environment. However, if the number of person is too many, like in this case, it will completely fail. Like you can see here at a certain point when they're giving money, you will see blah, something like this. This is still an open problem that we are working on. But yeah, we hope to see this kind of things as the next tool to navigate either on YouTube or other kind of scenarios. Yeah. Then I end this. Thank you.
Okay, so we're out of time officially, so anyone who needs to go, please feel free to, but we could probably take a question or two more if anyone's around. Any burning questions?
I think you can take the thing. I'm talking to him.
Oh, right. Do you have enough information there to stabilize the video, so as to remove the effects of the handheld cameras?
The stabilized. So the question is, can I, instead of doing this, can I stabilize the camera?
Well, do this as well, of course. But,
yes, stabilize the camera,
well,
yes. Yeah, actually, I don't have a video, but I generate that video, and that was pretty nice. Yes, you can use a stabilization. But there is a similar work that does this, right? I mean, I don't remember who was the author. They were doing something like this. They were applying structure for motion, and then they were using this kind of things on then the projection and stabilize the cameras in this way, but you can do it. I mean, it's similar to their approach in practice, this kind of things.
So my question was that if you do the dense structure if you take the dense structure from motion approach and also take stereo cameras, it might be possible to in fact generate sort of very high quality dense 3D reconstruction, and then the transition
dynamic, all dynamics, yes.
Exactly, and then there won't be a problem of actually making a transition, right? Any sort of view would be a rendering of the
and they also will work also with multiple multiple people. Yeah, so having having a dynamic reconstruction, it would be pretty nice.
Even for the one or for the single person case, what I realized is that you were computing the segmentation completely independently in each frame, right? If there was a central sort of model that was being accumulated,
it will be more accurate. Yes, absolutely. One thing about the reconstruction, the thing is this one. If we reconstruct the foreground, the question that we were thinking at that time, will we have enough accuracy to have nice visualization? Because currently the reconstruction does not have a quality that can give you nice visualization, right? So you are kind of, I mean, I was thinking this like, it's a kind of uncanny valley on this kind of scenario, right? I mean, it's, you're familiar with that, right? I mean, the idea is that the more accurate you go in the reconstruction, it doesn't mean that you will have a better perception of the result, right?
Yeah.
It can fall down, and I think it's happening also here.
So I was thinking about the scenario where if you take the Kinect Fusion approach, right, and basically if you see the video like Sharam is going around and
that is very accurate
So
reconstruction.
if you have 3 or 4 Kinect cameras now going exactly in the same sort of way, which are capturing the scene, creating a dense 3D model simultaneously from 3 or 4 things, and then you're making a transition, you can actually make a very dense transition because the scene has already been reconstructed to a very good extent, right? Especially for rigid objects, we don't know how to track how to do
You need to
for non-rigid objects, but for rigid objects it could be done very accurately.
Yes, I mean there is also some extension for non-rigid object. Yeah, that will be pretty cool. The only problem is that the common video cameras does not incorporate a Kinect, so I don't know if.
You could use there's stereo.
Yeah, stereo cameras, yes.
Which would work outdoors as well, where the Kinect would probably fail.
In that case, yes.
Yeah, it's a cool idea. And how far away are we from the YouTube scenario you mentioned? Because that would be awesome.
YouTube has some problem just for the data, because we didn't found, still we were not able to find at that time, and we still haven't found some multi-view scenario. There is a website that actually provides something for concert now.
Yeah.
And do you remember the name? I forgot it.
I forget the name.
I forgot also.
They do it for mobile phone cameras.
Yes, and you can camera switch, something like this.
Camera switch.
Switch.
It, yeah.
So, but in that case, you can just switch the camera.
Yeah.
That will be a nice extension. The only one problem is that the background in a concert is black, which means that you cannot calibrate at all. So we are.
Yeah. Yeah, the illumination changes might be a problem.
Yeah, the flashlights is very helpful because you can at least synchronize with them. So I mean, another idea, if you don't have a lot, you can calibrate with respect to the foreground by using a reprojection technique. But I'm kind of working and try to see if I have a solution for that. But I think we are dealing with a more interesting scenario, but I need to talk you offline for that.
Okay, great.
Because and I think yes. I mean, the thing that you were pointing out is that this is still not usable, and this is what we are working on, because the people didn't found an application, direct application of it, because also it takes a lot of time in the offline processing. And actually, the offline processing there is off in MATLAB, so we didn't run it for a lot of things. But I think we can have something working.
Yeah, that would be great.
Yeah, also in YouTube, the resolution is another problem.
Yeah, I was going to say, what's the current resolution that you're capturing?
This is full HD. No, it's full HD. We were not able to process full HD. It was too much data. So we just crop it enough. It was too much. Yeah.
Great.
Okay.
Well, let's thank you again.
Thank you.